Now, we've been talking about multivariate distributions for the last several lectures. We started off by talking about joint PMFs and joint PDFs, as well as joint CDFs for multivariate distributions. Most recently, we've talked about marginal distributions and how to obtain those marginal distributions from the underlying joint distribution. In this lecture video, we're going to start looking at conditional distributions and how to construct or derive those conditional distributions from the underlying marginal and joint distributions. So let x1 and x2 be random variables with joint PDF little f and marginal PDFs f1 and f2. Suppose that x2 is a value in the space of the random variable x2 so that the marginal PDF of x2 is positive when evaluated at that value of little x2. Then the conditional PDF of x1, given that the random variable x2 is equal to the specified value of little x2, will be denoted in the following way. We're going to use the same letter, lowercase f, but in the subscript we're going to have a 1 vertical bar 2, so this corresponds to the conditional PDF for the first variable given the value of the second variable. And then we'll have a similar kind of notation in the argument list. x1 is the argument, and then the vertical bar is read given, and then the value of x2. So this is the that is the notation for representing the conditional PDF of x1 given x2. It's defined in the following way. It is the ratio of the joint PDF evaluated at the particular specified value of x1 in the argument and the given value of x2. So here in the numerator we have the value of the joint PDF evaluated at x1 and x2, and then we divide that by the marginal PDF of x2 evaluated at the given value x2. In the same way, if x1 is a value in the space of the random variable x1, so that the marginal PDF of x1 is positive when evaluated at that value, then the conditional PDF of x2, given that the random variable x1 is equal to that specified value of x1, will be denoted in the following way. So again, we are using the lowercase f, and then we have a 2 vertical bar 1, so this represents the conditional PDF of the second variable given the value of the first. And we have an analogous notation here in the argument list. So the argument to this function would be x2, and then we are given the value of x1. We define the conditional PDF of x2 given x1 as the ratio of the joint PDF evaluated at those two values, x1 and x2, divided by the marginal PDF of x1 evaluated at the value x1. And so you can see in each case, we have in the numerator, we have the joint PDF. You see that in both these cases. And then what we're dividing by is the marginal PDF of the variable that we're conditioning on. So in this first definition where we are conditioning on the random variable x2, we're dividing by the marginal of x2. And in the second definition where we're conditioning on x1, we divide by the marginal PDF of x1. Now, as an exercise, what I would like you to do is to prove that these two conditional PDFs are in fact PDFs. And so be thinking about the definition of what a PDF is and just show that based on these definitions that we've given, that these are in fact PDFs. Now, when we talk about a conditional distribution, a conditional PDF, or a conditional PMF, and by the way, let me just go back and say that I'm using a PDF as a general term now. All right, this applies to whether we're talking about continuous random variables or discrete random variables. I could have broken this out and talked about conditional PMFs and conditional PDFs, But these definitions apply regardless of whether we're talking about discrete random variables or continuous random variables. So when we define these things, we really don't need to make that distinction. When we talk about conditional expectation, however, because the method by which we calculate the moments depends on whether we're dealing with discrete or continuous random variables, we will have to make a distinction. And in those situations, I may talk about a conditional PMF or a conditional PDF. So a conditional distribution is in fact a distribution. And so therefore, associated with such a distribution are various expectations, the same kind of expectations that we would have for the kind of distributions that we looked at thus far. So for example, we could have means, variances, skewness coefficients, kurtosis coefficients, and so forth for conditional distributions. And those characteristics, those quantities, are calculated via conditional expectation. So let's look at this for the context of discrete random variables first. So let x1 and x2 be discrete random variables, and let f sub 1 given 2 be denote the conditional PMF of x1 given x2. Then the conditional expectation of x1, given that x2 is equal to the specified value, x2, is denoted in the following way. Now, we do have to have a slightly different notation for this type of expectation, just to help remind us that we're talking about the expectation associated with a conditional distribution. And so this notation here is read the conditional expectation of x1 given that x2, the random variable x2, is equal to the specified value x2. And because we're dealing with with discrete random variables and therefore a conditional PMF, to get this expectation, we have to use summation. Now, let me just point out here as we go forward that the notation is going to get a little bit more involved and a little bit more cumbersome. But the concepts that we're going to be looking at here are exactly the same as the concepts that we looked at when we looked at expectation using univariate distributions and when we looked at multivariate distributions previously. The only difference is the notation. So when we talk about a conditional expectation, what that is, it's an expectation with respect to a conditional distribution. And remember that an expectation is just a weighted average. It's a weighted average of the values taken on by the function whose expectation we're wanting, and the weight factors are the values of the PMF if we're dealing with a discrete random variable, or the PDF if we're dealing with continuous random variables. So with that in mind, the conditional expectation of x1 given x2 is equal to the sum over the sample space of x1, and I've got kind of an abbreviated notation here, right, because things are getting more complicated. So this summation with an x1 down here, this represents a summation over all the values of x1 in its sample space of the product x1 times the conditional PMF of x1 given x2, and notice that we are conditioning on x2 here. So we're going to have a different conditional expectation for each value of let me back up. We're going to have a different conditional expectation of x1 for each value of x2. Similarly, if this notation, which is again, it denotes the conditional PMF of x2 given x1, then we can talk about conditional expectation of x2 given the value x1. And it's defined in a completely analogous fashion. The expectation, the expected value of x2, given that x1 is equal to this specified value x1, is going to be this weighted sum. All right, it's a sum over the values of x2 in the sample space of the random variable x2 of the product x2 times the conditional PMF of x2 given x1. And so the fact that we are conditioning on x1 shows up here All right, and so that's going to impact this conditional expectation of x2. And so we will potentially have different values or different expressions for this conditional expectation of x2 for each value of x1. Now, if x1 and x2 are continuous random variables, then the only difference in what we just talked about is that instead of summing, we're going to be integrating. So the conditional expectation of x1 given x2 is going to be the integral over the real line of x1 times the conditional PDF of x1 given x2, and we're integrating with respect to x1. The conditional expectation of x2 given x1, again, is going to be the integral over the real line of x2 times the conditional PDF of x2 given x1, and again, we're integrating with respect to x2 there. Now, more generally, we can think about the conditional expectations of functions of random variables. And so let g of x1 be some function of x1. Then the conditional expectation of this function g of x1, given a particular value of x2 in its sample space, is going to be exactly what we would expect based on our previous experience thus far. If we're dealing with discrete random variables, then the conditional expectation of this function g of x1 given x2 is going to be this weighted average of the values taken on by the function g of x1. The weight factors are the conditional PMF of x1 given x2. And we're summing these products over all values in the space of x1. If x1 is a continuous random variable, then we just replace this summation by integration so that the conditional expectation of g of x1 given x2 is going to be the integral over the real line, the integral with respect to x1 of g of x1 times the conditional PDF of x1 given x2. So again, remember that these concepts, even though the notation is slightly more complicated, just because it has to reflect the fact that we're conditioning, we're still working with distributions. They just happen to be conditional distributions. And so, these concepts are exactly the same. So don't let this slight increase in the complexity of the notation throw you off. Now let's look at some particular examples of expectations above and beyond the expected value of the random variable that we looked at 2 slides ago. For example, if we let this function g of x1 be this expression, x the square of x1 minus the conditional mean of x1 given x2. Okay, this is this expression here, the expected value of x1 given x2. This is the mean of the conditional distribution of x1 given x2. And so if we calculate the expected value of this, that's going to give us the variance of the conditional distribution of x1 given x2. We can also call that the conditional variance of x1 given x2. We would denote that this way, again, slightly different than the typical variance representation because we, again, have to show in our notation that we're dealing with a conditional distribution. And so this represents the conditional distribution of the conditional variance, of the distribution of x1 given x2. All right? And so if x1 is a discrete random variable, then the variance of the conditional distribution of x1 given x2 is equal to this. It's given by this sum. All right, the sum over all values of x in its sample space of the square of the difference between x1 and its conditional mean times the weight factors, which are the values taken on by the conditional PMF of x1 given x2. If x1 is continuous, then this conditional variance, the variance of the conditional distribution of x1 given x2, is obtained by integrating that same product instead of summation. So again, the square of the difference between x1 minus its conditional mean times the conditional PDF of x1 given x2. Now, I just want to point out that in the same way that the variance of a univariate distribution, there's a shortcut formula for that. There's also a shortcut formula for the conditional variance of x1 given x2. And so here we have the notation for the, again, for the variance of the conditional distribution of x1 given x2, also read as the conditional variance of x1 given x2. This first expression is the defining formula. It's the definition. But we can also calculate this using this algebraically equivalent expression. This first term here, this is the expected value, the conditional expectation of x1 squared given x2. And then the second term, which we subtract from the first, is the square of the conditional mean of x1 given x2. In other words, the square of the expected value of x1 given x2. So what I would encourage you to do is, just as a little side exercise, is to prove to yourself, write it out and prove it, that these two expressions are equivalent. Now, higher order moments, both raw moments and central moments of the conditional distribution of x1 given x2 are computed in an analogous fashion. So we could talk about obviously this expression here, and if I go back to the previous slide, okay, the expected value of this quantity is this is the second central moment of the conditional distribution of x1 given x2. We could calculate the third central moment of the conditional distribution of x1 given x2. We could compute the fourth central moment of the conditional distribution of x1 given x2. From those, we could then come up with expressions or values for the skewness of the conditional distribution of x1 given x2, as well as the kurtosis of the conditional distribution of x1 given x2. We could calculate the raw moment. So we could calculate, for example, here we see here, this is the second raw moment of the conditional distribution of x1 given x2. We could certainly calculate the third raw moment of the conditional distribution of x1 given x2, and also the fourth raw moment. In fact, we could calculate any raw moment for a conditional distribution, and it would be calculated in this way. So let's look at some examples. And I think what I'll do, because we're already at about 18 minutes for this, this video, and this is going to be, I think, a fairly involved example to go through. So I'm going to stop the lecture, this particular video, and start the example in the next video.